So first of all, you will need to recall some geometric facts. This is on page 314 and 315 of your textbook, and you need to know certain things, which we covered this year anyway. So you know the ideas of angles in parallel lines, some of the concepts of polygons. So this angles in parallel lines, this is year 8 work. In fact, you probably touched on it in some of it in year 7. It's the idea of those corresponding angles, co-interior angles, etc. So just quickly to provide that diagram, if you've got two parallel lines and then you've got a transecting line like that, these two angles here are equal and they're called corresponding. No, they're not, they're called alternate angles, sorry. These two angles here are equal and they're called corresponding. And these two angles here are equal, they're not equal, so those two angles are supplementary. They add to 180 degrees, okay? Is that all right, Alex? Yeah, okay, cool. So the last one is that this angle is equal to that angle and they're called vertically opposite. So you'll need to be able to draw on that information in this topic and in the circle theorem topic we get to. Polygons, you'll need to have an understanding of some polygons. And yes, so this looks a bit complex, n minus 2 times 180, but this is basically just a rule that tells you the number of sides minus 2 times 180 is the angle sum of the polygon. Triangle, 3 minus 2 times 180 is 180. A quadrilateral is 360, a pentagon is 540, a hexagon is 720, etc. You might have to call on that, but probably only really up to hexagon at worst. The triangle inequality, we talked a bit about this last week, but the triangle inequality is two sides have to be more than a third side in any triangle for any pair of two sides. Otherwise, if you tried to draw them, if you had the long side drawn and you tried to draw the other two sides and make them meet, they won't meet anyway. Pythagoras theorem, you should be aware of. And also just some basic idea of some quadrilaterals. So the principles or the properties of a trapezium, parallelogram, rhombus, rectangle, square. I wouldn't really sit and read that and try and memorise it. I would just have it with me, refer to it as you're doing this exercise, go back and go, oh, it says it's a trapezium, what's the property of a trapezium? Just make sure that you know it as you go, it'll be there. Congruence you won't need, and similarity you won't need in this topic at all. So I'll just leave it there, but it's worth sort of remembering the idea. Probably the main thing is that congruence implies that they are exactly equal, whereas similarity implies that one is an enlargement of the other. So they're exactly the same shape, but one's been enlarged. So that's the difference between congruence and similarity. So here is the stuff that you will need to know that might be new, it might not be. Two rules first of all. Collinearity and concurrency. 3 points are collinear if they exist on the same straight line. That's the first thing. I'm going to move on from this maybe too quick for you. So if 3 points are on the same straight line and the same straight line passes through those 3 points, they're called collinear points. It can be more than 3. It could be 4, 5, 6, 10. Concurrent lines, so this collinearity is to do with points, concurrency is to do with lines. So 3 or more straight lines are said to be concurrent if they meet at a single point. That might also be important because it might form the basis of a proof. So there's my two diagrams. Hopefully if you just remember those diagrams, it makes sense. And then here's a recall that section before I do the example. 5 dot points. The first two are pretty similar. So we did this at the end of last year, and it was actually probably the thing that caught you guys up the most, and we played around with it a fair bit. Two vectors are parallel if vector A is equal to a constant times vector B. Then they're parallel. One's just longer than the other, but they're in the same direction because K, that constant, doesn't change the direction, it just changes the length. This is the same. So AB, vector AB is parallel to BC. If vector AB is parallel to BC, then AB equals a constant times BC. Now it might be an enlargement, BC might be longer, but it might be shorter, so K might be less than 1. That implies though, because this is, remember, AB with an arrow is saying a vector joining A and B. And BC with an arrow is saying the vector joining B and C. This implies that A, B, C are collinear. Even though I could draw vectors, I could draw two vectors that are parallel that aren't collinear like that. Because B is common, that means that's B, it means it must look like this. So because B is a common point, as this diagram shows you, if AB and BC are parallel, then ABC must be collinear points. Okay? So that's a little link between collinearity and how that might look in terms of a vector proof. Two vectors A and B are perpendicular if and only if A dot B equals 0. You've just done that in your formative. And this one here, you might not quite remember it. I don't think it really comes up that much, but it does come up a little bit in some Pythagoras proof. So, and we can prove this again. We talked about it a bit, but we can prove it from this, A dot B, the A dot B idea. A dot A equals the magnitude of A squared. So A dot A equals basically A1 times A1 plus A2 times A2, which is A1 squared plus A2 squared. And the magnitude of A is the square root of A1 squared plus A2 squared. So you can get the link directly from that. That might come through if you've got a proof that involves Pythagoras theorem of magnitudes. But I wouldn't remember that. I would just, you can derive that. It might be on the formula sheet, I can't remember. And this one here, which we talked about briefly, and it comes up in a couple of the harder proofs. So the idea here is that this is if they're linearly equivalent. So if you've got two linear vector equations like this, so you're saying two vectors A and B can be combined as MA plus NB, that gives you an overall vector. If you then get PA plus QB and you say that they're equal, that implies the only way that can happen is if M and P are the same number and N and Q are the same number. It can't happen any other way. That's linear dependence. So again, that might come. That's like, it looks complex in this form, but hopefully, if you get to that point, you'll see it'll be obvious that those two must be equal, and you can track that across. Are there any questions on these? There's more detail on page 306 of the text, which I've written here, but that's just my little summary of it. So that's my uncomfortable pause to see if anybody has any questions, but on the video that's just going to look ridiculous. But anyway, we'll go with it. Example 1. This is the only example I do today. It starts easy, a little bit trickier later on. So example 1 says, in this diagram, so I've just drawn a triangle. Could be any triangle, because I'm not giving any values. You'll notice that more and more maths moves away from actually involving numbers, which is great. So in this diagram, AB is equal to the vector x, so we're calling this x. And BC is equal to the vector y, so we're calling this y. So we're just giving names to those vectors. It's AB, so it's in that direction, and it's BC, so it's in this direction. Determine CA in terms of x and y. So I'm hoping you see that if I start, this one is saying start at C and finish at A. Now, if I was in a car and I wanted to get from C to A, I would drive along this road. But I don't have any names for this road. I don't know what it is. It says here determine CA in terms of x and y. So the only way to come up with a name for this is to go along this path. And to go along that path, I'm actually going, so this is A, I'm actually going CA is equal to negative y minus x. I'm going backwards along BC, which is negative y, and then backwards along AB, which is negative x. To add a line into this, or add a couple of lines into this, so you could just write that straight down. It's a pretty trivial question, but you could write it like this. CA is equal to CB plus BA, and CB is the same as negative BC plus negative AB, and negative, now we're told BC is y, so it becomes negative y minus x. So we get the same answer, but that's a longer version of the answer that really steps out the proof, and it might be handy in some of the harder questions. Now it states, I'll do this bit in red so we've got it clear there. Let D be the midpoint of AB, so we'll just say D is about here, and E be the midpoint of BC. So E is there. Prove that 2DE, so here's DE, is equal to AC. So I want to prove that the length of DE is basically half of AC. And therefore that DE is parallel to AC. So that's the proof that I want to make. How much room have I got? That should be enough. So I'll do B here. So first of all, I know what CA is. which means I know what AC is. So AC is equal to X plus Y. It's negative of CA. Also, it's pretty trivial in diagram. Now, what I'm going to note on here is that if D is a midpoint, well then this is equal to a half X. And if E is a midpoint, this is equal to a half Y. So this is a pretty easy question when you break it down like this, because that means that DE is equal to DB plus BE. So again, I'm going to do this a slightly slower way. And I want to do it so it's got the diagram in there as well, but that's going to be tricky-ish. But I'll try. DE is DB plus BE. But we know that DB is half of AB, because that's what we're told in the question. And we know that BE is half of BC, because we're told that in the question. And that's equal to a half X plus a half Y. And then that's equal to a half of X plus Y, which is equal to a half of AC. And therefore 2DE is equal to AC, as required. Now, this is, it said show that. Did it say show that? No, it said prove that. No. It's more of a show that question because I've given you the answer. So it's not really appropriate here because you've been given the answer. And it's not really a form of proof, it's direct proof a bit, but with the vector ones it's not really appropriate to use QED, kind of. As required is fine though. But, I mean, really you're not going to lose marks for using QED. You'll just get a sad face from me. And 2DE equals AC, therefore AC is equal to A times DE, which means that AC is parallel to DE. All you need to show that two vectors are parallel is that one is a scalar multiple of the other, and we already had it here. We had that DE was KAC, done. So that was just an easy additional step. Any questions on that? The first few questions in the textbook exercise just get you to break things down in that triangle form or maybe a quadrilateral and get other lines in terms of X and Y and stuff like that. And the proofs come a bit later. So we've got a couple of harder examples to do on Wednesday.